Okay, so hello everyone. So welcome to our this week Rutgers Efficient AI seminar. And today we're very glad to have the Dr. Cheng Tan from the Arizona State and the Google to give us this talk, Hardware Software Co-Design for Efficient Acceleration on the CGRAs. And Dr. Tan is currently a software engineer at Google, and he works on the HTPU machine learning compiler. So this is a very, very important tool and the technique. And meanwhile, he is also a part-time research faculty member at Arizona State University. And Dr. Tan received his PhD from the National University of Singapore. Previously, he has held several positions at the Microsoft, Pacific Northwestern National Laboratory, Cornell University, and he contributed to the Brainwave ML accelerator compiler development and hardware software co-design and the network on chip research respectively. And actually, Chen, actually the bio you give me is pretty short and actually doesn't fully reflect your contribution to the community. So actually, Dr. Tan has made several very important contribution to the reconfigurable acceleration, especially for the CGRA, and he actually open sourced the several very important and useful tools. And he also won the Best Paper Award in several prestigious conferences like the ICCD and so on. Okay, so now let's welcome Dr. Tan to give us this talk.
Cool. Thanks, Prof. Yuan, for the introduction, and I appreciate the kind words. So we can see the screen, right?
Yeah, we can see the
Cool.
screen.
Okay. Cool. It's quite my pleasure to give this talk, hardware software co-design for efficient acceleration on CGRAs. And as Prof. Yuan mentioned, that I'm a software engineer at Google and also a research faculty at Arizona. And I have worked on the reconfigurable data flow accelerator for years. And most of my works are open source, and I have first order paper across almost all the top tier architecture related conference like ISCA, Macro HPC, SECAD, SECD, Date DAC, and so on and so forth. And I'm still actively review papers as a PC member for conferences and journals. And yeah, this is my research repository. Most are related to the reconfigurable data flow acceleration. And I'm still like quite open to any type of collaboration as long as you think your idea is cool and can put some engineering effort on this domain and push this domain forward. That's what I'm willing to see. So please feel free to contact me and join our community. Yeah, so now I'm not alone. I have a bunch of people we work together in this community for this topic. Yeah, so before diving into the details of the talk, I want to give some demo about our end-to-end framework for reconfigurable data flow acceleration.
Disables tile 5 and tile 10. Disables tile 12 and tile 3. Removes links between tile 0 and tile 15. Compiles kernel and maps, DFG. Updates to 2x2 tiles. Compiles kernel and maps, DFG again. Runs tests. Generates the S-Verilog. Synthesizes the RTL. Displays the layout.
Yeah, as this demo shows that this is a kind of end-to-end framework that help you to design data flow accelerator as you want, right? It originally give you a design template and you can manipulate the topology, functional units, functionality, and form any type of design and automatically generate a synthesizable Verilog and map a given kernel or map a set of kernels onto the design you just have and generate the layout using the open road backend. All sub components of this tool are open source, and yeah, it's also integrate different other tools like MacPad and the KickTie and OpenRoad and Palmetto, all MLIR, all those stuff to enable the end-to-end development. So today's talk is about first I will talk about why CGRA, and then I will talk about some background about the conventional CGRA architecture and compiler, and then I will talk about some advanced techniques built on top of conventional CGRA, but it's more domain-specific data flow accelerators, and then I will call back this toolchain. So first, why CGRA? So CGRA is energy efficient, more energy efficient than the CPU and FPGA, and it has higher system frequency than FPGA because and also less latency for dynamic reconfiguration. That is because CGRA is more coarse-grained. Instead of FPGA, it is more fine-grained, right, in the lookup table bit level. But CGRA is more functional unit level. And CGRA is more flexible than ASIC because ASIC is application-specific integrated circuits, right? It's only served for a single application. Even though nowadays some machine learning ASIC has some flexibility in terms of serving different sizes of the tensor, but it's still kind of fixed functional units, right? So CGRA in this context is more flexible because of its different functional units functionality. And the different papers already talk about the CGRA position across different platforms accelerators. We can see CGRA is always at this trade-off points between ASIC and CPU near the FPGA. And like this one, and also CGRA is here, right? So, but CGRA is not a fixed terminology. It contains different architectures. So in this talk, I categorizing CGRAs into 4 groups. And we can see these are the industry products and academic projects related to CGRA. And first is the systolic array. We know that systolic array is used to accelerate the matrix multiplication, right? It's hardware like some type of buffers and the data going through like top down and left to right. And the functional units inside each tile or PE is a Mac unit, which can do the multiplication followed by addition. So we view this systolic array as a subset of conventional CGRA because it has less routing opportunity and less functionality. And also similar to some other machine learning accelerator, it still kind of fixed the routing and the functionality, but it's different from the conventional CGRA in terms of the granularity. Like in machine learning accelerator, it's mostly accelerate the tensor stuff, right? Instead of scalar value. And there is also a spatial CGRA, which is like can include systolic array and the machine learning accelerators. So let's take a look. What is the spatial CGRA? Before that, let's see how spatial CGRA accelerate a kernel. So first, when you have a C++ kernel, this one is an example of a synthetic kernel. It doesn't mean anything, but just to show you how we accelerate it. And a kernel can be represented by a data flow graph. We can see here, like the addition is done here and the multiplication is done here. And this path is for the iterator increment. And this part is for the accumulation. And when you have a spatial CGRA, normally your CGRA should have more resources than the given kernel. So here the kernel has 11 DFG nodes and your CGRA has 16 tiles, right? And then you can map your DFG onto this spatial CGRA for acceleration. But note that it's not every cycle you can launch a new iteration here because there is a inter-iteration dependency, data dependency across iterations. So normally you can only start the next iteration after 4 cycles to meet this dependency. So this is about the spatial CGRA, and it's kind of a superset of all the stuff I mentioned before. And it has some advantages, like it's simple mapping. So map this DFG onto this CGRA is kind of like shortest path finding problem, right? And this CGRA has less hardware complexity. Each tile only need to do one operation during the entire lifetime of the application. However, it also has some drawbacks, like it has lower utilization. You see some tiles are kept in idle for the entire time. And another drawback is cannot accelerate a kernel that has larger resource requirement than the provided architecture. So this motivates the spatial temporal CGRA, which we expand the architecture in the time domain. This example shows how we perform the acceleration on the spatial temporal CGRA. Same kernel with 11 DFG nodes, and the given CGRA has only 9 tiles. And we can see for cycle 0, you can map 2 nodes here. Cycle 1, map these 4 nodes here. Cycle 2, and then cycle 3. And eventually you have 4 cycles. Each cycle have different DFG nodes mapped onto it. And this II means initiation interval, which means every 4 cycles, you can start the next iteration. So this type of expanding on the time domain can help you to accelerate a kernel that has larger resource requirement than the provided architecture. So it improves the utilization, and it is more flexible and more can be used in more general scenarios. But it has drawback, like the compilation is complicated this time, right? Because you have another domain to map your compute operations. And the architecture is a little bit more complex because for this one, each cycle you can change your operation, right? So like this tile in cycle 0, you execute N1, which is 5 in the LLVMIR operation. And the next cycle, it runs this modulo, like N3. So it's like a trade-off. So here I put the spatial temporal CGRA as a superset of all this stuff. And then there also another type of CGRA or reconfigurable data flow accelerator, event-driven. So instead of just based on the data or single kernel, event-driven, you can switch like context switch, or the task ID is embedded in the data. And once the data come, you can choose which task you want to execute. Like this Cerebrus accelerator is kind of event-driven. And if you look into their programming guide, you can see that there is a task ID, and there is even color, right? Like each color corresponds to one task ID. And when the data comes, it will like select the task need to be executed based on the task ID embedded in the data payload. Right, so these are the different categories of the CGRA, and it's a kind of like one include another, and event-driven, I think, is the most powerful but most expensive. So let's see what is the conventional CGRA architecture. Normally it looks like this, a CPU and a CGRA fabric, which loosely coupled with each other, and the CPU can issue the command like launch it to perform the acceleration. And similar to the other machine learning accelerator or GPU or FPGA, normally you need to bring the data, preload the data onto the CGRA fabric, the SRAM first. Or there may be some other advanced technique that you can do the dynamic reconfiguration or dynamic data switching, right? Data loading and spill something. Yeah. And for a conventional CGRA accelerator, it normally contains multiple tiles and multiple SRAM banks, and a subset of tiles can access the SRAM banks for load store operations. And you need some other control routing to preload the configuration into each tile to notify it what it need to execute in each cycle. And for the microarchitecture of each tile, we can see there are multiple functional units, memory unit, or adder, multiplier, or even complex functional unit perform the MAC operation, right, or other fused operation. And a set of registers here and a crossbar here to perform the data routing across tiles, and config memory, as I mentioned, they host the, you can call it instruction or control signals, notify which functional unit need to be invoked for each cycle's execution. So what is the conventional compiler look like? So given a kernel, and it can represent as a data flow graph here. And first we can do loop tiling. This is useful because sometimes we have a large kernel, right, working on a huge chunk of data, but your accelerator only has a limited SRAM, right? So loop tiling can help you to tile your loop and evoke your accelerator multiple times in order to fit the application kernel's data into the limited on-chip SRAM. And here we can also do the loop unrolling. If your kernel is pretty small, right, most of your resources are keep idle. So in this case, we can unroll the loop, and then each iteration, you have more compute operations need to be accelerated, right? Here we can see we have more instruction level parallelism, right? So here we can map this larger DFG onto the CGRA fabric for acceleration. So you can have better utilization. And then represent the C++ kernel or LLVMIR into the data flow graph, and then map onto the provided CGRA fabric as I showed before. And then you can perform the power performance area evaluation given the RTL or our toolchain, the synthesized Verilog. Cool, that's pretty much about the conventional CGRA architecture. And now I want to show some advanced techniques around the conventional one. And the first is the operation and topology related technique, which is Aurora in I think is date 2021, automated refinement of coarse-grain reconfigurable accelerators. So Aurora provide a design template that helps you to design any CGRA architecture for a given domain. Domain means that a set of kernels. So here we can see that this template contains more than enough routing resources and functional units. So this is not a fixed RTL now. It's kind of parameterizable RTL template, and you can manipulating this routing to form any topology. You can manipulate the functional unit to form any functionality. So here we can see it can form a conventional CGRA by removing the diagonal connections here, right? And each tile is the ALU perform the basic functionality like addition, multiplication, shift, and so on. And it can also form a systolic array, right? By removing the redundant connection like bottom up or right left, just to keep left right and top down, and keep limit the functionality in each tile as MAC operation. We can form a systolic array design. It can also form some other strange or advanced design in proposed by other papers, like a CCA like accelerator 20 years ago, if I remember correctly, and a Marie like accelerator. It's yeah. So in this way, it can form any accelerator design you want. And so its compiler is still like the conventional one, but we add a backward loop here to, based on the evaluation results statistics, we can perform the loop tiling and the operation fusion again and again until your design converge, like until your target is met. Your target could be the power budget or some performance requirement, and this entire procedure can be done thousands of times, and to achieve optimal design you want. So this compiler tuning first, you give target application kernel, and based on the size of the kernel working on, you can shrink the design SRAM size, and by perform the loop tiling, and then you can check whether the resource is underutilized, whether you want to increase more resource in order to enable better speed up. But the trade-off is the area and the power, right? But that depends on your target or objective. Like if you have more area budget, you can tolerate more resources. So you can enable this loop unrolling to see whether it's worth it. And then you can do the operation fusion, like this multiplication followed by addition. You can fuse them as the MAC operation. And correspondingly for a specific domain, if all this type of operation, it's kind of a common operation, right? You can like fix your tile with this MAC operation, like a systolic array, instead of provide more than enough ALU functionality here. So this kind of tailoring your architecture. So all these things are done automatically with a simulated annealing engine. And as a user, you just need to provide the objective, budget, and the tuning will help you to form a target design given a set of kernels. So Aurora achieves the better performance across all the different selected accelerators for specific domains. And we for this part, the evaluation get the power performance area. We use the open road to feedback the target or the budget or constraints. Yeah, that's the Aurora work, which is a fundamental design template used for the other following work. However, Aurora didn't consider the SIMD, right? The vectorization, which is a very common case for existing machine learning or some other linear algebra or GPU like style application. So here we propose the WACPAC, a vectorizable and precision-aware CGRE, enabling vectorization. So similarly, application kernel can be mapped onto a small CGRA, like a 2x2 CGRA. And if you are given a larger CGRA, right? So this time you wanna like expand your DFG, make it has more instruction level parallelism by loop unrolling. However, loop unrolling, you can see that here is like a longer inter-iteration dependency, which can decrease the overall performance. So we can perform the vectorization on this kernel. Instead of loop unrolling, we can vectorize the kernel. And in this way, we don't need like a larger CGRA fabric, but still keep the smaller size in terms of scalability. But note that this time each tile can perform SIMD operation, right? Not the scalar operation anymore. So overall, the size may be still similar for this 2x2 and this 4x4. But here we can see that after applying the vectorization, there are two types of the operations. One is vector operations, the other is scalar operations. So by that I mean like vectorizing a kernel, normally leveraging the LLVM vectorization path. It's not all the operation can be vectorized, right? You still have some unvectorized, like the iterator related iterator increment or some like a compile branch control related operations, but some computation related can be vectorized. So in this way, motivates the hybrid design. Like for WACPAD, the CGRA design is a hybrid. The vector tiles and scalar tiles interleaved with each other. And for vector tiles, we have multiple SIMD fashion, SIMD lanes, right? Each one is 16 bits. And this 16 bits can be fused together to perform like a 32 bits addition. This idea is borrowed from the bit fusion in ISCA 2018. And this 16 bits can even like form a 32 bits adder. So for multiplier, it's a little bit different, right? You need a 16 bits multiplier to form one 32 bits multiplier. Yeah. So, but like for this type of fusion, this is a kind of a trade-off between the accuracy and the speed up, right? If your application has a higher accuracy requirement, you need a longer beat width, right? But if you have your application domain has lower accuracy requirement, you can enable more vectorization factor. So for the compiler in Backpack, it's still similar to the previous one, but we have the loop vectorization here, and the user can trade off the accuracy and the vectorization factor. And the evaluation results shows here, like we can have lower accuracy when you enable higher vectorization factor. Yeah, that's pretty much about the Webpack enabling vectorization. But can this help large language model? So recently we have a paper called Pikachu, plugin CGRA handling upcoming nonlinear operations in LLMs in SPROS 2025. So here we show that the nonlinear operations in LLM are evolving daily or weekly or monthly. And the nonlinear operations account for a considerable amount across models in terms of the overhead. Like here, we show that the linear is like 60%. So the nonlinear is the rest. And also here, based on the like, I believe this is the Llama 2, and within specific sequence lenses, the nonlinear operation ratio increase. But this kind of distribution would change depending on your model or the model size and the model architecture and the sequence length. And for all the nonlinear operation, even though they are different and evolving daily, but they share some basic operations like division, exponentiation, invert, sine, cosine. And for the data flow, we can categorize them into element-wise operation and also the reduction followed by element-wise operation like softmax, norm. So, and also for the trade-off between the accuracy and the performance, right? It's well known that nowadays people leverage the quantization or integer operations rather than the floating point. For example, here exponentiation, exponentiation is can be replaced by integer exponentiation with Taylor expansion here. So yeah, we also leverage this into our CGRA acceleration for the nonlinear operation. So based on the findings we just mentioned, the CGRA here in Pikachu is kind of a hybrid design. So some operations are commonly appear in all the nonlinear operations. So we form our functional unit to support the most common operations, most common fused operations, like the addition followed by addition, compare followed by selection, MAC operation, and so on and so forth. And also to support the floating point and the fixed point conversion, which is used pretty popular for linear and the nonlinear. The bridge between them, we need to support this type of conversion in our functional unit, and also we have the lookup table embedded in the functional unit to support such acceleration. And also, as I mentioned before, the Webpack, right? We can trade off the accuracy with the vectorization factor or vectorization speed up. Here we also leverage the same stuff and enabling the that trade off between the accuracy and the speed up. Oh, yeah. And this, as I mentioned, Pikachu is a plug-in CGRA accelerator, which is like plug-in at the end of the C-study array. So, or maybe GPU, like it doesn't matter. It's a plug-in accelerator. So as long as your linear operations result can go into this CGRA fabric, it can help you to perform the nonlinear operation. But well, in this case, the interface is important, right? So we need a shared buffer between the linear and the nonlinear fabrics. And here we show different execution or data flow fashion for this type of integration. like the systolic array results can directly goes into it through double buffer and consumed by CGRA, or if you have a very large results, right, you need to spill the results into host and then get it back into the CGRA for the following nonlinear operations. So different types of data flow are accelerated by this paper. Then there is the compiler toolchain to enable this nonlinear operation in LLM. So given a machine learning model, we can lower it through the MLIR compiler. And this is the linear affine dialects. And then scope out the nonlinear part and the linear part. Linear part is done by the systolic array or GPU or any linear accelerator, and nonlinear part will be accelerated by the Pikachu accelerator. And the user can trade off, can define, right? If you want a higher precision or lower precision, which one you want. This kind of an inference quantization or like inference time decision depend on your application tolerance in terms of accuracy. So this part of machine learning lowering to accelerator is previously published, also proposed by us, called the ML CGRA. It's an integrated compilation framework on top of MLIR. And then once you lower to LLVMIR for the nonlinear operation, you can do the conventional thing like unrolling vectorization and DFG generation and map onto the CGRA. This part is the conventional LLVM CGRA compiler I mentioned before. So Pikachu shows that we can achieve better performance, but with acceptable accuracy loss across different machine learning models. And Pikachu outperforms the state-of-the-art Gemini and Tandem accelerator, which both of them are able to perform nonlinear operations, if I remember correctly. Yeah, at least the Tandem can do it. Yeah, that's pretty much the domain-specific accelerators, and we also have many other topics related to the CGRA or reconfigurable data flow accelerator design, like our hardware generator OpenRoad. We write the model in Python, or it's a kind of a parameterizable architecture template, right? That can help you to automatically generate the synthesizable Verilog. And the power efficient CGRA in 2021 HPC, the ultra elastic CGRA. This one is a spatial only CGRA, but like you can manipulate the DVFS on the CGRA in tile level. And there is another advanced version called the EST. You can, instead of a tile level DVFS, we want to like cluster multiple tile together because DVFS also add some overhead, right? So there's a trade-off between the performance and power and the DVFS overhead. And this one is a temporal spatial CGRE. And as I mentioned before, machine learning model, Onyx, PyTorch, all of them can be lowered onto CGRA leveraging our MLIR tool. And also we explore the dynamic resource allocation in HPC and 2022, and we also have the deck paper like accelerate FHE, which is a security domain using CGRA. Cool. Then let's call back our CGRA toolchain. As I mentioned before, a machine learning model can be lowered through the LLVMIR. So here you are free to plug in any existing MLIR passes like loop, affine in the affine dialect, the tiling or some affine related loop transformation, right? And then you can do the conventional CGRA kernel manipulation or transformation optimization, like tiling, vectorization, and routing in LLVM. And then, as I mentioned, we have the hardware generator, which is built on top of Palmetto. We provide the basic functional units or module, like the tile memory unit on chip network, and regist files, crossbars of them, and automatically perform the testing with, we even have the hypothesis testing, which use a software way to verify your hardware in Python, right? If it's in Python, it's pretty much easier than write your test bench in Verilog. And then we can evaluate the synthesizable Verilog. And we also provide the GUI to chain integrating all the mentioned stuff to facilitate your development in this CGRA research. And there are lots of ongoing works, like we are trying to visualizing the model lowering in MLIR. And also we are migrating this LLVM part kernel mapping into MLIR, because I personally believe MLIR is more suitable for such data flow acceleration mapping. And also for the hardware generator, we are defining the ISA and developing the simulator to make it even faster instead of in the Verilog world. And also we are increase the functionality and the flexibility by supporting the event-driven, like the CGRAs or some other conventional data flow architecture. And also for the GUI part, we are trying to integrate the AI engine, AI agent to automate all this procedure, like minimize the human being interaction to automatically generate a design given a machine learning model or a set of kernels or a target application. Yeah, so there are lots of ongoing work in progress works, and as I mentioned before, I'm open to any type of collaboration. If you are interested, please feel free to contact me. Cool. So the takeaways for this talk is like we at the beginning I mentioned that CGRA is not a like outperforming any other accelerators, right? It is a kind of a trade-off in between. Depends on your target, your budget, or your domain. You can tailor your CGRA architecture to meet your own requirement. And CGRA has a different categories. It's not a fixed terminology, in my opinion. It can be even larger, or you can view it as smaller, like systolic array or spatial only, but it can be larger, right? And different types of data flow accelerator can be related to it. And our goal or our end-to-end framework is to make user or anyone, anywhere, anytime be free to create their own reconfigurable data flow accelerator based on their own requirement. But conventional CGRA has its own right conventional architecture, like loosely coupled, but there's still also tightly coupled CGRA accelerator there. Many years ago proposed like tightly coupled into the CPU pipeline. And also CGRA has its like mesh like topology to connect different tiles for data routing, and each tile has different functional units to be selected at runtime to perform a different acceleration with reconfigurability. And compiler is very important in my opinion. It's not only because I'm a compiler engineer, but we see that NVIDIA like achieve lots of progress or draw lots of attention these days, right? Because their CUDA is easy to program, right? Their hardware easy to program using CUDA, and the CUDA kernel can be easily mapped or dynamic scheduled or enable the SIMD multi-threading easily, right? So compilation is very important, is a key role in this ecosystem. And previously we have some like companies like yeah, I just mean like if we can make this part better, we can push this domain further. So we put a lot of efforts into this like machine learning model lowering or general application C++, lowering into the data flow graph and then map onto the CGRA fabric. And there are lots of ongoing work. We want to make this robust. And CGRA, as I mentioned before here, right, it's a trade-off point here, and achieve a better power efficiency than CPU and achieve better flexibility than ASIC. And this is our toolchain, and the QR code is linked to this repository. If you are interested, please just play with it. And if you want to contribute any related topic or publish paper or collaborate with us, please feel free to contact with me. Yeah, that's wrap up my talk. Thanks.
Thank you, Chen. Thank you very much. So this is quite comprehensive work that's for the CGI. Yeah. So I have several questions, but first I would like to ask you for the audience. So if you have any questions right now, you can unmute yourself to ask, or you can input your questions in the chat box. I think maybe I can ask some questions first.
Mm-hmm.
So first, it's kind of quite general question. So because if you go back to your slides, that you first you use some examples to show a simple synthetic code and map on the CGI, right?
I mean this one.
Yeah, something like this. Yeah. So for this synthetic code, it seems that so for each different tires, sorry, for each operators, you map that to one tire, right?
Yes.
Yeah. So, but we know that for the like operators, so it kind of the imbalance like the cost.
Mm-hmm.
For some operators, they make kind of the very complicated and require more
Yes.
resources that. So I was wondering, so whether you consider such kind of imbalance. So for sometimes maybe we need some to use the more tiles to support one operator.
Yes, that's a common question or research topic. That's why here, like as you mentioned, maybe the compare is pretty easy, but floating point addition much complex, right? So each tile for this case, normally that's a trade-off. Each tile contains multiple functional units, so it contains both the comparator and also the adder here, and then you choose one, right? Like during the after you launch the kernel. So it's not like, so each tile is this kind of a homogeneous CGRA. Even though you map different operation onto it, the hardware is homogeneous. But as I mentioned before, for the Aurora work, right, the design template, you can tailor your architecture. Like if you see all your kernels, like you don't need addition in this tile, then you can delete that hardware unit from it, right? So that's an extreme case. Like if you want only accelerate single kernel, right, then this CGRA becomes the ASIC. that's why I call it a trade-off, or like it's a design space you can tailor based on your interest of the kernels. That's that answer. Yeah.
My question is that I understand that so the overall architecture is kind of homogeneous.
Mm-hmm.
I was wondering, so whether some specific algorithm that how to like to allocate so one like big operators across the multiple.
Yeah, so we also have ongoing work, like whether you wanna like fuse these two together to make it balance with this one, or like fuse these four together, like operation fusion, right?
Yeah, this kind of
yeah.
the resource allocation and the kind of the partition.
Yes, that this is kind of a partition in design time, and then after you partition or fuse them, you need some like analytical model or go through the synopsis cadence or open row to get some feedback, right? To see whether this balance is does that make sense or not, and then towards optimal design. Yeah. Yes.
Okay. Yeah, I have some other questions, but it seems that there's some questions from the chat box. Yeah.
Oh. Let me check the chat box. The demo that you used in the which one is that? The demo is for the CGRA flow. Let me put it in the chat box. Right, it's here. So, thanks for the interest. No problem.
Some other questions from the audience? Yeah, and actually I have some more specific questions. For the Pikachu work, you mentioned that, so you show that, so the breakdown of the different type of the operations as the length increase. So actually, I'm a bit surprised that so as the sequence length increased, the portion of the linear operations it actually further kind of reduced, because so like we know that for the attention, so it is kind of the quadratic operation with the sequence length. So typical.
Yeah, that's a good question. I have the same question when our student performed this evaluation at the beginning, but this performance evaluation is done in GPU. And so GPU did the, as you mentioned, did the MATML convolution pretty well. That's why it requires some less time. And this also like within some specific model and within some specific like a model size. Like for, as I mentioned, if we have a larger model size, right?
Thank you.
Then this figure will be changed. So it's kind of on this for sequence length, it has this type of behavior in evaluated in GPU. Yeah.
Okay, thank you. Yeah, and a further question is that so actually so this is kind of the comparison. So because I once heard some discussion about that. So how do you think about that the CGI as kind of the like some new more reconfigurable feature from the FPGA, like the overlay and so on?
Yeah, that's also a good question. What I saw is I believe like hybrid is the trend. Like FPGA, right? Also have the AI engine today, right? It's kind of like conventional FPGA fabric plus the coarse grained reconfigurable accelerator. Like a risk, they even have a RISC-V core to map different accelerators, the different kernels onto it. So also like our CGRA, right? We are also trying to embed the lookup table into the functional unit here, right? To perform those like type conversion or some exponentiation, sine cosine stuff. So I would say in terms of the research, maybe hybrid is always direction we can go, and it depends on your accelerating domain, right? Like whether this kind of a hybrid makes sense. You can still tailor your architecture if you have like a budget or target in terms of performance or area. That's kind of design space exploration, I would say. So that's why we have this type of tool provide more than enough design space, and we are trying to leverage the machine learning to automate this kind of pruning or searching in the design space towards the best design, right? So that's a topic, and we are putting effort onto it.
Thank you. Thank you. I think there's another question in the chat box.
Thanks. It's great to see you further expanding my question when is in with some parallels such as okay and B parallelism of for examples of max. Yeah, I think that's a good question. If you look into the different machine learning accelerator, there in industry, normally there would be specific functional unit to accelerate the nonlinear operation, and also for the PIM or something, right? Like there some papers from Stanford or Tsinghua University, they embed the CGRA onto the PIM for acceleration. So here the example I show is kind of a simple example to show the benefit by extracting the instruction level parallelism and also the loop pipelining, right, to enable the speed up. But if you can think about multiple CGRA together, and maybe there is an on-chip network connecting them, I would say there are like lots of parallelism. And also that requires the ecosystem, like I mentioned, that enable the SIMD, right? Instead of each functional unit is SIMD unit, you can also view each CGRA as a SIMD thread, right? So that's a kind of, I would say that's a pretty much many opportunities there for you to explore. And we are also have working in progress for this topic. Cool, that's a good question.
I think there's another question in chat box.
You're seeing and want to talk about AI agent. Most time it's offline. What is the function of will be there? Most time, okay. It can automatically change the mapping when input data is dynamic. Yeah, I would say, in my opinion, the AI agent is just do the human beings work. Like as you mentioned, is offline. So the design time is offline, right? You design your CGRA offline, but instead of you manipulate this, click those buttons, or automatic or manually launch some compiler, synopsis, cadence, compiler, the AI agent can help you to do it. So what is the so I mean, like the AI agent should be able to call the compiler, as I mentioned. Then it can automatically collect the results, right? So that's how it will be automated.
Any other questions from the audience? So then maybe I can ask the last question. So, so Chen, so in your today's work, so I think your major application is targeted for the AI machine learning. So definitely, so this is right now the top one application that in the hardware community. So I was wondering, so in the future, so do you project that what is other some kind of the potential application that the CGI can play an important role there?
Yeah, I would say like I'm a computer architect, not only like a machine learning acceleration engineer. I also like focus on like target the general kernels acceleration, and also our work is more like provide a like a toolchain or design space explorer for different kernels, no matter what their target. But for conventional CGRA, I would say there is a limitation in terms of the memory hierarchy. So which means like if it's a compute intensive kernels, right, it probably suitable for instruction level parallelism or loop pipelining. But if it's a data intensive, right, then I think we need to put some effort in the memory hierarchy or how the CGRA integrate with the, you know, the SRAM or DRAM or communicate with host or the other heterogeneous IPs in the SoC. That's maybe some new requirement to accelerating the the data intensive application. Like, yeah, so that's my opinion. Yeah.
So do you think that in your mind there's some other applications that may become more suitable for CGI?
Yeah, and in that specific context, I would say like if your application has some reconfigurability requirement, right? That will be pretty suitable for CGRA domain, like different quantization requirement, data type, and AR, VR, like imbalanced workloads. Like each iteration, it has a different behavior, like a ray tracing, you see a different ray, different color, different filter. So yeah, if any domain has such requirements, I would say that may be an interesting kernel or application for CGRA acceleration.
Thank you so much. So I think we can discuss that offline there.
Sure. Yeah.
There's so many kind of the interesting topic we may collaborate.
Yeah.
Okay. So any other questions from our audience? Okay, so if no more other questions, so let's thank our speaker again. Thank you so much, Dr. Tan. So this is a very, very interesting, amazing work and very comprehensive framework. And congratulations to your achievement on this. Yeah.
Yeah. Thank you, Prof. Yuan. Yeah, I appreciate the kind words. Yeah. Thank you.
Yeah, and also so thank our audience again. And so our next talk and also the final talk in this semester will be this Friday. So our so this Friday will be our last efficient AI seminar talk. Okay, for this semester. Okay, see you guys. See you this Friday. Okay, so thank you, Chen. So thank you so much. Have a wonderful day.
Yeah. Thank you. Thank you, Prof. Thank you, guys. Bye.